here we go. Let's put this over here. Let's oh shit, I don't need this one. Hopefully maybe that was doing something. Okay. Alright guys, let's get started. So, welcome to the Reinforcement Learning Workshop. Alright, that's, okay, so, my name is Zarar, and I'm the Director of Reinforcement Learning at RyersonAi. I'm going to be the one hosting this workshop today. So, there's a couple things I have to let you guys know. So, there is a bit of latency. The stream is like 5 to 6 seconds behind. So if you have a question, please be specific about exactly what you're unclear about, because I might not be sure about what you're referring to. So if you just say something like that was unclear, can you please repeat that? I might not know exactly what you're referring to. So be specific in the questions that you ask, and I'll try to do my best to answer them. There's also going to be a bit of buffering that we're going to have to deal with. If it does buffer for a while, just try to let me know, and then I'll try to repeat what I said to fill in the gaps. You know, this is our first Twitch live stream, so there's obviously going to be some technical difficulties, but just bear with us, and you'll have fun. All right, great. So, what is the roadmap? What are we going to be doing during this workshop? So this workshop is composed of 6 parts. The first is the introduction, which we're in right now, in which we're going to talk about the roadmap and the objectives for the workshop. So what we hope to achieve by the end of it. Then we're going to go into what reinforcement learning is. So we're going to define it. We're going to look at it. We're going to look at a bird's eye view, essentially, of what reinforcement learning is. Define some of the main concepts and make sure we've grasped conceptually what it is we're trying to do in reinforcement learning. Then we're going to jump into the theoretical background and as well as the implementations. So what we're going to do is we're going to go through a little bit of theory, and then we're going to implement it in Google Colab. And before we start this, we'll make sure everyone's on the same page about where we're doing it, and we'll make sure everyone has the right copy of the Colab file and all of that. So we'll figure that out before we start programming. So don't worry about that right now. And then, so we're just going to go piece by piece through the theory while implementing it at the same time. Then we're going to go through a demo of what we've been doing at the Reinforcement Learning department. We're going to show you a demo of an Atari game called Breakout, in which we implemented deep Q learning. So it's Q learning, but extended with neural networks. It's essentially what you're going to learn today, but combined with neural networks. And just combined with neural networks, yep. Then we might do a Kahoot if we have time. I'm not sure about the Kahoot. It's yeah. And then we're going to conclude with some announcements about events that are coming up for RyersonAi, as well as some closing statements. All right, great. So, what is the objective for this workshop? So the objective for this workshop is to introduce you to reinforcement learning. So what that means is explaining to you guys what reinforcement learning is, the problem it's trying to solve, you know, some examples of it in the world around us, and then also a simple approach to solving that reinforcement learning problem, called Q learning. But if I'm being completely honest with you guys aren't going to leave experts in reinforcement learning, and you guys probably won't even leave knowledgeable in reinforcement learning. You know, it's not really possible to compress this entire field into some 2 to 3 hour workshop, which is why, although we're going to be going through the theory and stuff like that, which is why that's not my intention. And that's not what I think workshops are about. So what I think workshops are about are giving you some hands-on experience with the technology, but mainly focusing on showing you why this technology is worth your time. why showing you why this is something you should be learning about. And that brings me to my intention for this workshop. So what my intention is to show you the value of learning about reinforcement learning. Uh, I want to show you why you should be studying it, why you should be reading about it, why you should be learning it, implementing it, practicing it, all this stuff. So there's two main approaches I can take to doing this. The main approach is probably the common approach, in which we just talk about some of the possible applications of the technology. And in the case of are literally endless, right? If you believe that there's nothing magical or about intelligence, like there's nothing like intelligence is just fundamentally just information processing. Hopefully it's not. Yeah. So if you think that there's nothing really special about intelligence, like there's no magic involved, there's no other force that we don't really understand or something like that, if you believe that it's just fundamentally information processing, then you must also accept that it's possible to on computers. Because what are computers if not just machines that process information, right? So if you accept those things, if you accept those premises, then which you don't have to, right? It really might be the case that intelligence isn't just information processing. Intelligence might be something else. There might be something that we have yet to discover about how intelligence works. That all might be the case, but right now it seems that intelligence is just information processing. And if you accept all of that, then you have to accept the conclusion that it's possible to write computer programs that can do anything can do. So this ranges from very simple tasks like classifying images into different classes, like this is a monitor, this is a phone, this is a pen, this is a keyboard, right? All the way to very complex tasks like performing surgery on someone, diagnosing someone with a disease, uh, driving a car, delivering food, all the way to things like performing or doing scientific research, right? If you accept the things we talked about earlier, all of these applications, scientific, engineering, system design, are all potential applications of this technology, and that's very exciting. Um, so what are we having stream issues? Uh, yeah, alright guys, I'm sorry guys, we're just gonna have to bear with this. Ah, damn, that's unfortunate. Alright, so let's keep going. Alright, let's keep going. Sorry, where was I? Yeah, so if you accept those things we talked about, then all of these things are potential applications of reinforcement learning, which is very exciting, right? Just imagine a computer program called Albert Einstein that we could just run thousands of instances of 24/7. That's insane. Just we would progress so quickly, right? There would be breakthrough after breakthrough like almost every day if we were able to write computer programs that can do scientific research. So that's all well and good. That's a very interesting. That's probably the I've thought about. Yikes. So you guys have probably thought about these things on your own, and that's why you guys are probably here. You guys are interested in this field because of these things, and so that's one approach we're going to be taking, talking about these applications. Now, uh, another approach that we can take, an approach that isn't taken as often, to showing you the value of learning about reinforcement learning, is talking about the insights that it can provide into what we are and what intelligence is. Reinforcement learning is Yeah, so it can provide a lot of insight into what it means to be human and what intelligence is fundamentally. There's a lot of concepts in reinforcement learning that have been borrowed from animal behavior, from animal psychology, I should say, and because of that, there's a lot of parallels between what we're going to learn today and our own experience, our own lives. And we can actually pull a lot of these concepts we learned from reinforcement learning and apply them to our lives in ways that just improve the quality of our lives or improve our own understanding of our own lives. All right, so hopefully everything's good. Hopefully it's not lagging as much. Uh, all right, let's proceed. Okay, so here we go. Let's get started. So what is reinforcement learning? Reinforcement learning, this is the definition. It's a subfield within machine learning that is concerned with programming software agents that learn how to act in an environment in a way that maximizes some reward. Alright, so there's quite a bit there, and what we're going to do is we're going to try to dive into each of these terms in a bit more detail so we really grasp what this is trying to say. So, what is machine learning? So, reinforcement learning is a subfield within machine learning, which itself is a subfield within artificial intelligence. Now, what AI is, what this field is simply just the field of computer science, subfield within computer science, that is concerned with writing computer programs that can do things that require human intelligence. Right? So this ranges from very simple tasks to very complex tasks, like we talked about earlier, right? Image classification, talking, art, right? Creative tasks as well, driving cars, all of these things, right? This field of AI includes all tasks that require intelligence. Now, if you were to try to solve this problem, the approach that most of us would probably take is some sort of rule-based approach. What we would do is we would come up with some rule set and give it to the machine. We would say, follow these rules and just do what the rules tell you to do. So, for example, if we're looking at an example of a self-driving car, we might say, if there's a pedestrian on the road, hit the brakes. Right? That's an example of providing the machine with a rule for it to perform some sort of intelligent task. Akinator is actually another example. I'm not sure if you guys have played the game or if you guys remember, but it was a game that determines what you're thinking, right? And to most people, it seems like it's intelligent, but really all it is just a really massive decision tree. It's just a bunch of rules. And what it does is it uses this decision tree to determine exactly what it is you're thinking about. So, what machine learning is, it's a different approach to solving this problem of AI. So instead of writing rules like we would do in other approaches, in machine learning what we do is we just throw a bunch of data at the machine, and we say, you know what, you figure it out for yourself how to do this task. So let's think about an example of machine learning. So say we're trying to get a computer to classify images into different classes. Say we have a couple different classes, right? Like dogs, cats, cars, planes, computers, people, all this stuff, right? We have a bunch of different classes, and what we want the machine to do is to classify images into these classes. So we want the machine to determine what the picture is of. So is it a picture of a dog? Is it a picture of a cat? Etc. So in machine learning what we do is we just give the computer a bunch of examples. We don't give it any rules. We just give it a bunch of examples. Like, here's a million pictures of dogs. Here's a million pictures of cats. Here's a million pictures of humans. You go figure out for yourself what you think, or you go figure out for yourself how to achieve this task. And what the machine does is it goes through all of this data and learns how to recognize dogs and cats and planes and cars in images. So it learns how to do the task from data. And that's how it differs from other approaches to this task of artificial intelligence, this problem, I should say. Now, reinforcement learning is a subfield within this subfield, right? So it's still trying to do the same thing, which is just write computer programs that can do things that require intelligence, but it differs from some of the other approaches in machine learning. So in reinforcement learning, we don't really give it any data. We actually allow the agent, the computer program, to interact with some sort of environment and gather data on its own. So self-driving car simulators are probably the best example. So what you do is you let the self-driving car agent interact with a self-driving car simulator, like Carla or something like that, and then by interacting with the simulator, by gathering data from the simulator, the the computer program learns how to do the task of driving a car. Alright, so hopefully that's clear about the big picture of what we're trying to do in this field, of what AI and reinforcement learning is and how they all fit together. Alright, great. So reinforcement learning is a subfield within machine learning. Great, we defined that. That is concerned with programming software agents that learn how to act in an environment in a way that maximizes some reward. Alright, so what's a software agent? So a software agent is simply just a software version of an agent, right? But what's an agent then? An agent is just an object that takes as input some information, uses that information to make a decision, and then takes an action. So this is an agent. An agent is an abstraction, right? There's a bunch of real-world examples of agents, and you can include anything that just takes an information, makes a decision, and then takes an action. So we are agents, right? We take in information through our senses. We see, we hear, we smell, we taste, we touch, right? And then we use all of that information to make a decision about which action to take. So if you're walking down the street and you smell something good from a bakery or something like that, that causes you to make a towards the bakery and then eat the food or whatever, right? That's just an example. Now software agents are just the software equivalent of are the software version of agents, right? So software agents also take in information in the form of data, right? So just ones and zeros, and it uses that information to make some decision about how to act, and then it takes that action. So in software, the data looks a little different and the actions look a little different because software agents interact with computers instead of the world. So the observations might be just like stock price data or something like that. The agent processes this data, uses it to make a decision about how to act, then it takes that action. So buying or selling the stock, turning some valve off, right? It can if it's like managing some sort of factory, it could turn a valve off to control the rate of production of some product, right? These are just examples of agents in software. So great. Hopefully, what software agents are clear. Okay. Hopefully that's clear. And so now what? So software agents that learn how to act in an environment in a way that maximizes some reward. So this diagram right here is essentially what reinforcement learning is. It's a visualization of reinforcement learning. So in reinforcement learning, we have two main components. Here we have the agent, which we just talked about, right? Something that just takes in information, makes a decision, takes an action. And we have the world. The world can be defined as just everything that is not the agent. So if we're looking at this from our own perspective, we would be the agents, right? Taking actions, making decisions, etc. And the world would be everything else. So the world would include other people, the world would include your stuff, your phone, everything. And what we do is or agents, I should say, observe the world. They observe some information about the world. It can look different for different agents, right? This is just this is just a very general definition, but it just observes some information, processes that information, and decides and makes a decision about which action to take, takes that action, and observes the next state as well as a reward signal. So in reinforcement learning, what happens is that the agent tries to maximize this reward signal. All right, so uh, give me 1 second. So what I hope to have shown you guys by the end of this workshop, or one of the things I've hoped to have shown you guys, is just the generality of this diagram, of this way of looking at the world. We can think about other people, about animals, about everything through this perspective. We can think of other people as agents that are just observing states, taking actions in a way that maximizes some reward. And there's a lot of benefits to thinking about other people like this. There's a lot of benefits to thinking about animals and other agents through this lens. Whether it's true, I'm not entirely sure. We behave in a way that can be described like this. We behave in a way as if we're maximizing some sort of reward signal, but this might not really be true. It might not really be exactly what's going on, but it's a very powerful approximation that can provide you with a lot of insight into yourself and into other people, and it can allow you to, and it will help you make better decisions. This observation, this workshop essentially, is I hope going to help you guys make better decisions about the actions that you take. All right, okay. Okay, let's keep going. All right, so let's look at some examples. Let's look at some examples of this generalization in the world around us. So, training a pet is probably the most common and obvious example, right? So in this example, we have an agent, and that is your pet. It's either a dog or a cat or whatever other pets you guys have, and we can model the dog's. We can model the dog using this perspective, right? So the dog observes states, uses that, it makes a decision, takes an action, and then receives the next state, observes the next state, and then receives some reward signal. So when you're training your dog, you might want to train it to come back when you call it, right? I think this is referred to as recall, right? When you call your dog, you want it to come back to you as soon as possible. So how would you train your dog to do this? So let's look at that example through this perspective. So you call your dog, and what happens is your dog observes the state, and that state includes you calling it. So it might be some auditory information about hearing its name or something like that. And then the dog has to decide which action to take. And the dog can take a bunch of actions, right? The dog can continue playing with other dogs or doing whatever it was doing. It can do nothing. It can just start barking randomly, right? It can just randomly just take a shit. It can also and it can also come back to you, right? The action that you want. So the agent would then take that action, whichever action it wants, and then it would observe the next state as well as a reward signal. Now the dog, being a learning agent, will do the actions that give it a higher reward signal. So if you give your dog a treat at the right time, it will reinforce these actions that you want it to be taking. Right? I think we all agree with that, and we all in some sense know that our dog, given treats at the right time, will take the actions that we want it to take. That's how you train your dog. So that's an example of reinforcement learning in the world around us, at least for animals. Now, training a human is also another example of the same thing, of reinforcement learning in the world around us. So we're constantly training each other. I know this sounds a little weird because I put it right after training a pet, but I want to show you guys how similar these two things are. So how do you train a human? How are we training each other? Social interaction is probably the best example in which we can see that we train each other. So say you're hanging out with your friends, right? You guys are maybe at a bar, maybe at McDonald's, wherever, right? And you are listening to a conversation, you're participating in a conversation with your friends. Now what you're observing is maybe what they're hearing, what the other your friends are saying, maybe their body language, maybe their facial language, maybe their facial expressions that you're perceiving, that's being inputted into you. Now what you do is you use that information to determine which action to take. And what the actions you could take are maybe doing nothing, maybe saying something, maybe changing your facial expressions, changing your body expressions. There's a huge set of actions that you can take in social interactions, and also a huge set of observations. Then what we do is we take an action, we observe the next state as well as a reward signal, and this reward signal influences our behavior. So say you're hanging out with your friends and you guys are just having a regular conversation, and then you decide to make an off-color joke, right? You just make some risky racist joke. Maybe I don't know. I'm not going to give any examples, but you just make some joke, right? And then what happens is the world, you take that action, and then you observe the next state as well as this reward signal. Now, if your friends didn't like the joke, what they would do is they would give you a negative reward signal, and this is usually in the form of maybe a negative facial expression, maybe a change in body language. Maybe they'll say something to you like, "Hey man, that wasn't cool. You shouldn't be saying stuff like that." And then this reward signal influences our behavior so that next time we might not take that action. Or we might not, we might be less likely to take that action. Or maybe if the joke landed and your friends laughed at the racist joke, and your friends laughed at the racist joke, that might actually reinforce your decision to make those types of jokes, right? So that's an example of how we train each other, and we ourselves are getting trained by other people. Okay. Another simple example, a quick one, is just uh, uh, in the workplace, right? You're an employee in the workplace, and you are talking to your clients. You are hearing stuff from your clients, talking to your boss, etc. And you are taking actions. You're working hard. Uh, you're working hard. You are, maybe you insult your client, maybe you insult your boss, all these things, right? And then you take these actions, and the environment sends you a reward signal that influences your behavior. So your boss might incentivize you when you work hard by giving you a raise or a bonus or something, and that makes you modify your behavior, that makes you change your decision-making process so that you take that action more often. It reinforces that action. So hopefully that's clear. What I wanted to do in this slide is show you guys some examples of this generalization in the world around us, and show you guys how it's a very good model for thinking about ourselves. When do we get to the cool stuff? We're getting to the cool stuff, man. Like 3 slides from now. Alright, so here we go. So now what we're going to do is we're going to talk about Markov decision processes. So Markov decision processes are essentially the mathematical formulation of this visualization, right? It's just a way of us talking about this stuff mathematically. Alright, great. So what Markov decision processes are discrete time stochastic control process. So discrete time is hopefully clear. Essentially what it means is that between any 2 time values, there's a finite amount of time steps. And then what a stochastic control process is a index set of random variables s, a, and t. S, a, and r. Okay, so these are all random variables, and they're sampled from these sets called R, A, and S, A, and R. So what S is a finite set of all the possible states that the agent can be in. So yes, it's pretty clear. It's a set of all possible states that the environment can be in. We'll go through some examples. And then A is just a finite set of all possible actions that you can take. And then R is actually the set of all real numbers. What the reward signal is just a real number. So what happens in Markov decision processes is that you sample this index set. You sample trajectories from this index set. So this is an example of what a trajectory might look like. You might sample S naught, A naught, R naught, all the way to some terminal state. For today, we're only going to be dealing with episodic environments, meaning environments that have some terminal state. There are environments that don't have a terminal state, but like the stock market and stuff like that, but we're not going to focus on those today. Okay, 1 second. All right, yeah. So these are subscripted T because they're indexed by the time step that the agent was in when they observed that state, took that action, and received that reward. Yeah, yeah, yeah. Um, so T is a subset of capital T, which is also a random variable. This index set can have variable length, uh, depending on how many time steps you sampled, right? So, for example, like okay, so now let's look at an example of let's take a look at a tic-tac-toe example. So what the state space would look like is the set of all possible configurations of the world. So the set of all possible configurations of this tic-tac-toe board. If you guys so what the number of states is actually 3 to the power of 9, right? Where there's 3 different states that each square can be in, and there's 9 different squares. The action space is the set of all possible actions, so that would be like O here, O here, O here, X here, etc. And then the reward function is something we define. It can be something like plus 10 for winning and minus 10 for losing. All right, so yeah, so now let's look at the world that we're going to be dealing with. So we're just going to talk about the world real quick, and then we'll start. Maybe we'll take a break. I don't know. I think we're going pretty quickly. We'll just keep coding. Do we create the state space? That's a good question. It depends on how you define the observation. So if you are, for example, say you're creating a robot, a couple different peripherals you can give the robot. It is a huge amount. But we didn't create it. It's created by the environment, right? The state space. It's a complicated question, but it depends on how the agent observes the world, or what type of information the agent observes about the world. If the agent observes, just say camera input, right? The state space is actually pretty big. If it's it would be the set of all possible images that the agent could perceive, which is a massive set. But it's created by the observation, what information you observe. So here we're observing the board, and the board can be in 3 to the power of 9 different configurations. Okay. So we're going to be dealing with a simple environment called the taxi environment. We're dealing with this environment because the state space is small. It's only 500 different states. So we can use just regular Q-learning. But when you start to work on more complex reinforcement learning problems, the state space gets much, much bigger. So for Atari games, for example, you might have a grid of 180 by 180 by 3, right? It's just an RGB array. And the state space is just every possible image that could be generated. Every possible array between 0 and 255. Every possible array with values between 0 and 255 for each element. So it's actually a continuous space. It's actually, so it's in some sense it's almost infinite. It's depending on theoretically it's infinite. So when you start working with problems that have much bigger state spaces, you have to start using function approximators, like neural networks. Unfortunately, we're not going to get into that today because that would have it would have been too much to just throw at you guys. So what we're going to do is we're going to apply Q-learning in a small state space, but what you learn can be easily extended to these much more complex problems by using function approximators. And a few other things, but we'll talk about that after. Alright, great. So here's this environment. We are a taxi. The agent is a taxi driver, and the agent has an objective, and this objective is defined by this reward function. Because the agent is just trying to maximize the reward that we get, the reward signal is what the objective is. So the reward signal is you receive plus 20 points for a successful drop-off and lose 1 point for every time step. And there's also a 10-point penalty for illegal pickup and drop-off actions. So clearly from this reward function definition, the objective is to pick up and drop off the passenger in the fewest number of time steps. Because there is this -1 for every time step, we have to take the fewest number of actions to maximize that reward signal. If, for example, the reward signal was just like plus 10 for every time step, and -20 for successfully dropping off the passenger, the taxi driver would never pick up the passenger, because the taxi driver is just trying to maximize the reward function. The reward function is what determines the behavior of this taxi. Okay, so in this environment there are 4 different spawn locations. The agent can spawn at any one of these locations, and the drop-off location will also be spawned at any one of these locations. And what we have to do is we have to go to the spawn location, pick up that agent, and then go drop him off at the drop-off location. And what we're going to do today is we're going to write a computer program that just starts with a random policy, just some random rules, and then gradually figures out how to pick up the passenger and where to drop the passenger off. Alright. Forget the break. Actually, yeah. How many people are? 69. Okay. Yeah. Forget the break. Let's just keep going. Okay. So we're about to start the implementation. So, hopefully you guys have already opened the Colab file and made a local copy for yourself. So this is my copy that I get to edit. I should also make a local copy instead of editing the skeleton. So just save a copy. Open a new tab, and then just close the other one. Then you can rename this to whatever you want. I'm just going to rename it. Keep it copy of taxi skeleton. Alright, I'll give you guys a second to get set. If any of you have any questions about what we just talked about, or about the Google Colab and stuff, just let me know, and I'll clarify what I can. Alright, if you guys are good, send a thumbs up in the chat. Or do we have thumbs up in this? Send a lol. Yeah, just send one of those if you're ready to go. Ready to go? Great. If you're having trouble accessing the, use your Ryerson email instead of the your personal one. Nice. Okay. All right. So we'll wait a few minutes, and I guess we will take a break. Just if someone has to, if you guys have to like use the washroom, get some water or something like that, go for it. So guys, pull up the cheat sheet. It should be in the drive. Or I have a tab there. Yeah, the cheat sheet is in the drive. So this cheat sheet, it should have all the functions that you need for for today. So let me explain how we're doing this this workshop. F- From the state image, it seems like there are some actions at specific states that we cannot do. How does our taxi driver figure that out? Do we okay, that's a very good question. So that is so what what Prozipal is saying it brings up a great point. There are states in which we can't take specific actions. Like say the taxi was over here, right? In this state, the taxi cannot go down. It can go left, but this I think it gives them a negative reward. All right, guys. Okay, so that was a great question. The environment defines what happens when you take actions, right? Not the agent. So if we were writing the environment, we would have to define what happens when you take an action that doesn't really work. So here, if the agent was supposed to be was in this grid location, it can't go down. So instead of giving a negative reward, what the environment does is just returns the same state that the agent was in. Instead of like, but if we were defining the environment, if we were creating the environment, we could make our own rules, right? We can make it so that if you take a wrong action in this state, you actually just get a massive negative reward because you're literally driving onto the curb. right? But so it depends on who made the environment and what the environment rules are. So a very good question. Uh, so where was I? I was talking about the uh, the implementation, right? Let me close this. Uh, Great. So what we're going to do in this implementation is I'm not really going to be walking you guys through it. What we're going to do is you guys are going to encounter cells, so you can run the first one. So hopefully everyone's back. We're going to get started. If you fall behind, I should if you fall behind, check the solution file. Okay. So we're going to run the first cell, and this is just importing the libraries that we're going to be using. So Gym is OpenAI's library for reinforcement. Gym.openai. It's a great library that has a bunch of different environments in it that you can train reinforcement learning agents in. This is going to take a. Okay, great. And so this is what we use to. So it has a bunch of these Atari environments and these control environments, these robot environments, all this cool stuff. Uh, so we're going to be using this library to create the environment and to interface with the environment, to take actions in it, to observe states in it, and all that stuff. There are a few functions for Gym in the cheat sheet that you're going to have to use to do all of this stuff. Then we're using another library called NumPy. NumPy is just a library for numerical computation. It just has a very powerful object called an ND array, a NumPy array, that what it essentially is, it's like it's a tensor. It's a multi-dimensional array, a multi-dimensional matrix that has very nice properties, very nice functions and all this stuff. You'll see it as we go on. And then there's also a cheat sheet for NumPy in the cheat sheet. There's also some functions in the cheat sheet for NumPy. And time we're just using for something else. It's not important. So here we go. Let's get started. Initialize the environment. So use the cheat sheet. Figure out what you have to do to initialize the Taxi v3 environment. And then after you guys have had a go, I'm going to write down whatever my solution is to this. It's probably going to be the same for most of them, and then we're going to keep going. Alright guys, so this one was pretty easy, so I'm not going to give you guys that much time. All it is gym.make taxi taxi v3. So this takes as input the environment name from some set of environments that's on their website, right? About all these environments, and then it creates a gym environment object, and then it returns it to you. And this gym environment object has a great interface for training learning agents, which is why we're going to be using it. And we don't want to be writing the environments ourselves for now. Great, so you can run that. Great. So the next three I'm actually going to do with you guys because I didn't write it in the cheat sheet. The observation space from the environment, what you have to do is you have to write environment.observation space. The observation space is an attribute of the environment object, and then if you hit run for that cell, so Shift Enter runs it for those who haven't used a Google Colab before, or you can just click this square or this circle. Sorry. So, what is the observation space? The observation space is a discrete set of 500 different states. So this is telling us the size and type of our space. So what does this mean, right? So what this is saying essentially is that there's 500 different possible configurations that are all distinct from each other. So where did they get this 500 number from? Let me show you. So no, this is not it. So they're saying the environment is telling us, the environment object is telling us that there's 500 different configurations that this world can be in. So how did they get that number? So first of all, there's 25 different locations that the taxi can be in, right? It's a 5 by 5 grid, and the taxi can be at any different one of these locations. So for sure, right now we have 25 different possible locations of the taxi. Now, the passenger can also be in 5 different states. 5 times 5 times 4 times 5. Actually, let me keep going. So this taxi can be in the taxi can be in 25 different locations, right? And the passenger can be in 5 different locations. It can be here, 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 or here, but it can also be in the taxi. So what we have is 5 times 5 times 5 times 4. The 4 comes from the 4 different possible drop-off locations. So if we do the multiplication, 5 times 5 times 5 times 4, we get 500. Okay, hopefully that's clear. Let's keep going. So now let's look at the action space. We're going to write environment.actionSpace, and this is going to return what the action space is. Now, the action space is actually a discrete set of 6 different actions. Why is it 6? If we go back here, there's 6 different actions the taxi can actually take, not 4. So I see where you got 4 from. It can go up, down, left, right. But it can also pick up the passenger, and it can also drop off the passenger. Those are 2 additional actions that we have to account for. So the taxi can go up, down, left, right, pick up, drop off. That's the action space. And what the agent has to do is it takes as input the state, so just an integer between 0 and 500, and it has to figure out which action to take, which one of those 6 actions to take. And what we're going to do is we're going to write a computer program that learns almost the optimal policy. We'll see. Okay, great stuff. So, any questions so far? Are we all clear? We good? Great. Okay. So now what we want is we want to extract the number of states and the number of actions. So what it look like? So it's defined in the docs for this particular environment. If we go to taxi view source code, so whoever creates the environment defines the action space, defines the state space, and all of this stuff. So if we go down here, the action space is defined right here. There are 6 discrete deterministic actions, meaning when you take that action, that's exactly what happens. So you can go move south, move north, east, west, pick up, drop off. And for us, it doesn't really matter. Thank you so much. Great. For us, it doesn't really matter because we don't really care. We just giving it the set, and it figures out for itself which action to take in the right space. So for us, it doesn't matter. We don't need to know exactly which one is which, but it's nice to know. So now what we want is we want the number of states and the number of actions. So to extract that information, we do observation space dot n, which is this just extracts the number of observations, and then action space dot n. So I should say that the term observation space and state space interchangeably. The state of the world and the observation might not always be the same thing, It depends on how much information your agent has about the world. So, for example, in this case, the observation and the state are exactly the same thing. The Because the agent has access to the entire world. But say, for example, a self-driving car example, right? The the self-driving car doesn't know the entire state of the world. All it knows is a single observation of the world, just some subset of the information. So what we would use in more complex cases is we would be more careful about the terms we're using. We would use observation space in environments where the agent doesn't know the whole state, but just observes a part of it. But for now, because we're dealing with simple environments, observation space and action space can be used interchangeably. Observation space and state space can be used interchangeably. All right, let's keep going. Cool. Okay, so let's run this. Let's see what's going on. So great. So we have 500 different actions and 6 different states. So what we just did is action space objects. These were space objects, or actually discrete objects. But what we wanted was just the integer of the number of states because we're going to use them later in our program. So here we go. Now what we're going to do is we're going to talk about the components of the reinforcement learning agent. So if you guys have finished with the Google Colab, please return to the well, you were probably already on the Twitch. Please return to the Twitch tab, and we're gonna go through one more slide and then return to the code. All right. I'm assuming you guys are fine. Let's keep going. So, the main component of the agent is called a policy. It's called the agent's policy. And the policy is the policy. It's essentially just the agent's way of behaving in the world. More formally what it is, it's a function mapping states to actions. It takes as input, so for our taxi example, it would be an integer between 0 and 500. And then it outputs an action that the agent should take. So it maps from the state, from the set of all states to the set of actions. Takes as input the state that you're in and outputs one of the possible actions that the agent should take. That is what the policy is. For now, we're only dealing with deterministic policies, but when you deal with more complex problems, you might have stochastic policies, meaning the policy outputs not a single action, but a probability of the actions that the agent should take. And then what we do is we sample from this probability distribution to figure out which action to take. But considering how simple this environment is, we're just going to be dealing with a stochastic policy. All right, great. Now, all right, guys. Hopefully you guys aren't experiencing any, or hopefully the networking issues aren't too bad. So I'm going to proceed. So now what we're going to do is we're going to hop back to, and what I want you guys to do is I want you guys to, using the cheat sheet and the NumPy module, I want you guys to write a, I want you guys to initialize a policy randomly. So the policy we start off with, so just initialize a random policy essentially. So this one's a little tricky, but let's see if you guys can figure it out. I'll give you guys a minute or two. Damn, I'm sorry, guys. Uh. So, just to get a sense of where you guys are at, how many of you guys heard about the so are you looking at the solution? Let people try, and then I'll explain what the solution is. All right, so hopefully you guys gave it a try. Uh, Hopefully you guys aren't experiencing yeah, harm. Okay, so numpy.random. So we're using the random module from the numpy library, and the function is randint. So this function takes in two values, a low value and a high value. So the low value would be 0, meaning a 0, and the high value would be a number of actions. And then the size would be number of states. So what we want is, so let's run this. So what we want is we want a particular example is we're representing our policy as an array, as a vector. Because the state space is small, because the state space is just 500, we can actually just fit it all into a vector. So we can have a vector of 500 different elements, where each element refers to the action that we should take in that state. So for example, this might be the fifth state, right? So I don't know exactly what the fifth state looks like, but there is a fifth state, or there's a state that is referred to by the by 5. Right? And what this policy is telling us is that when you're in that state, take action 0. Is that clear? So why would the high be 5? The high is actually 6. Did I write 5 in the solutions? I hope I didn't write 5 in the solution. Uh, so so there's 6 different values in this array. It can be 0, 1, 2, 3, 4, 5. So 6 isn't in it because we're including 0. Uh, so now what the task is? Can you explain more? Of course. Okay. So this is an example, this def policy, Python function. A neural network is another example. But the example we're using right now, the implementation of this policy is a vector. So this vector is of size 500, where each element refers to the action that the agent should take in that state. Right? We can actually input the state, say the state is 45, and then output the action. So we're not going to print it. This is just me showing you guys. You guys don't have to write this. Action is equal to, so the action that the agent should take in state 45 is just what the element is of this vector, the 45th element. And then we can print this action. Initial policy. And the action is 3. So what do we have? We have this, essentially now. Takes as input the state, right here. It's taking as input the state, and then outputs the action that the agent should take. I hope that's clarified things. Any other questions? Yes. Yes, Prazi. The policy defines what action that takes at each state, and this is just a random policy. So we'll talk about the initialization of the policy, but what we do is we start with the random policy, and then what we're going to do is, yes, very good, yes. The initial policy will be modified by the algorithm to get the optimal one. So what's great about Q-learning, you don't need to really know anything about the or you don't really need to have a good initial policy. You can start with a random policy, and you're actually guaranteed to converge to the optimal policy. I'm not going to prove the guarantee, but the policy, if you were to run Q-learning for an infinite amount of time steps, you are guaranteed to converge to the optimal policy. But you can't always do it practically, but in theory, it's you can start with a random, you can start with a terrible one. This could be all zeros for all we care. This could literally be initial policy is equal to numpy dot random numpy dot zeros. Sorry, what? Yeah, it could just be numpy dot zero number states. And then we could print this. It really, okay, this is important. Really, what the point I'm trying to make is it is just we can randomly initialize it, and what we do is we improve this randomly initialized policy until we get to one that performs really well. All right, so hopefully we're all okay. If you have any questions, please ask. Okay, moving on. So now what we're going to do is we're going to write this function called generate episode. Or you're going to write this function called generate episode, okay? What this function does is it takes as input a policy, and it, using Gym, it steps through the entire environment and generates that Markov trajectory that we talked about earlier. It's not really in the same form as the last time we looked at it. Let's go back. But essentially what we're doing is we're sampling one of these trajectories. Uh, the trajectory that the agent gets by following this policy. And this is just so we can see how good our policy is and how well our policy performs. What we're going to do is I think we use this after, but this is just to get a hang of. Okay. Um, so this is just to get a hang of how Gym works, of Gym's main functions. And I'm not sure if I don't think there's any NumPy in here. No NumPy in here for you guys. This is just to get a better handle on how Gym works and how we interface with the environment. So you guys have all the functions in the cheat sheet. What I want you guys to do is fill in all the question marks. Yeah, go for it. Well, I'll give you guys a few minutes. This one is there's a couple. Ash, are you using the did you make a copy of the Google Colab? Because that has at the top this import statement. So if you imported it properly like this, import numpy as np, and you ran the cell, you shouldn't be getting that error. If you are, um, if at any point, guys, you guys are getting errors, what you guys should do is you guys should come to runtime, and then just restart and run all. Or restart and run, I should say. Just restart runtime, and then just go run all the cells again. So it would be something like this: restart runtime, yes. This resets everything, and then what you would do is you would just run each cell to the point that we were at. Are you using the let me just type. Are you running all the cells? Oh, observation space. That's um yeah, you have to run each. So you guys so this is something called a notebook, and a notebook operates a little differently than a regular code file. If you had a regular .py file, what you would do is you can just run all of it, and when you run it, the file you have to run, right? But in these notebook files, what you have is you have these cells. You have text cells and you have these code cells, and these cells can run independently of everything else. So I can run this cell and this cell, but not this cell. This is very powerful for just programming in general. So you don't have to run everything again just to run one thing again. But the problem is you have to make sure you ran everything uh, before you run the cell that you're specifically on. If you're getting this observation space not defined, run this cell. If you run the cell and then you keep going, then the problem should be gone. All of them. No, run all of them. Run all of them. Okay, guys, we are gonna proceed. Hopefully that guy figures it out. Uh, I so how was that? That wasn't too rough, right? This is a pretty easy one. So here, what we have to do is we have to render the world. So how this function starts is it takes as input the policy. All right, and then we have this episode array, this list, I should say. And in this list, we put the states, actions, and rewards that the agent observes. So essentially, this episode is the trajectory. I could call this trajectory. It might have been more accurate if I called it trajectory, but nonetheless, this is what it is. It's not in this exact form. I did reformat it a little bit, so it's easier to code the things we're about to. But when you think about what this function is doing, it's doing this. It's using this policy to interact with the Markov decision process, and then sample and save the states, actions, and rewards that the agent encountered and received. The debug one was difficult. Yeah. Okay. So here it's simply environment.render. The action is policy st. Right? So when we reset the environment, we end up in some initial state. And in the taxi world, the initial state is random. It's not always the same initial state. Like tic-tac-toe, for example. Tic-tac-toe, the initial state is always the same. It's a clear board. But in this taxi example, the initial state is a little different. The taxi might spawn at a random location. The passenger might spawn at a random location. The drop-off location might spawn at a random location. So that's why, yeah, so this is just random. So then what we do is we render the environment. If render is true, right? If we input render true, we want to see what's going on. And then we determine which action to take. And this, what we do is we input the state that the agent is in into the policy, and the policy outputs the action. Right? I explained this a little bit in detail earlier. Hopefully that's clear. If not, ask any question. Ask any question you want. Then we use a function called environment.step. Actually, I should have explained this reset function. So this reset function essentially resets the environment to the initial state. It clears everything that happened, all the actions, and then it resets it to some initial state. Sometimes that state is random, sometimes it's not. But for our case, it is. So that's what this reset function does. This render function draws the environment to the screen. Unfortunately, more complex environments like Atari don't render on Windows and don't render on Colab. So if you guys do end up deciding to play with Jim and stuff, you have to use Linux to actually be able to see the renders. You can find some workaround, but it gets a little messy. Great. So now we figured out which action to take by referring to the policy. This policy is just inputted into this generate episode function. So here we go. Now this next line is returns these four things. The next state, reward, whether the environment is done or not, for episodic environments at least. And then this is just some additional information that you might need for debugging. But ooh, did okay, let's keep going. So great. So now we took that action and we saw the next state, received the reward, done, debug. Great. And now what we do is we append this to our Python list of the episode. So but what we're doing is essentially we're appending the state, the action, the reward, and the next state that the agent encountered. This is just to make things easier for us, and you'll understand this later on. Yeah, but this is just for our own purposes. But this is the same as this trajectory over here. That's the main takeaway. Now what do we do? Now we set the current state to be equal to the next state because we're going into the next time step. This is obviously a while loop, so this is the loop that the episode loop that runs until the episode is done. So we make the current state equal to the state that we ended up in, and then we do this so that this policy outputs the right action. Hopefully this is clear. Then we render again, and that's it. Now this should be good. You have to run the cell, right? Shift Enter or click this play sign, and now we're going to call this function. Generate episode initial policy render is equal to true. Alright, so I want you guys to run and look at how the agent interacts with this environment. So how the output is rendered, it renders each different state. It renders in ASCII code, but yeah. Oh geez, this was terrible. Alright, so what happened? So the agent ended up in this initial state. Whoa. The agent was in some initial state, right? Hopefully you guys are all looking at your own output. The agent ended up in some initial state, and you should see a rectangle with the taxi labeled as the yellow rectangle, and then the blue letter is the pickup location, and the pink letter is the drop-off location. Now, if you scroll down, you can see below the next state the action that the agent took. And if you keep going, you can see how your agent interacted with his environment. And because we all initialized the policy randomly, the policy sucks. The policy for mine is just doing drop off randomly at some random location. It's just off. It's nowhere near the passenger. It just keeps dropping off. This is obviously not the optimal policy. This is our initial policy. And how the environment works is it goes through, I think, 200 time steps. And if you haven't figured it out in 200 time steps, it just ends the episode. It just terminates the episode because if the environment were to let you go on for an infinite amount of time, the episode might never end. Because my agent is just clicking drop off. It was just taking the drop off action. So if the agent was allowed to go on for an infinite amount of time steps, it would, and it wouldn't move. It would just keep dropping off. So great. We have an initial policy. We have a function that generates a trajectory by using this initial policy. Yeah, yay, 200 drop-offs, right. And it turns out the policy sucks. And what do you expect, right? We initialized it randomly. So now, what we're going to do, we are going to do some reinforcement learning. What reinforcement learning is about determining the optimal policy. Okay, let me deal with a few different things here. So yes, Prazi, you're right. The ST1 will be the best way to do this is to actually print it out. Let's print it out. Let's print out the first couple of time steps, right? Because this is a NumPy array, it has very nice slicing functionality. That's why NumPy arrays are just great. So what we're going to do is we're going to output the first 3 time steps and all of the elements. Oh, sorry. I spelled it wrong. We're gonna do this. I'm gonna turn render off for now because I don't want to see the. Oh, sorry. I don't want to see the terrible performance. So I rendered it, and now what I'm gonna do is I'm gonna create a cell underneath it. Hopefully, I'm not going too fast. I'm gonna create a cell underneath it, and I'm gonna call episode, and I'm gonna slice it. I'm gonna slice, get the first 3 elements, get the first 3 time steps, and grab all of the elements. So here we go. What do we have here? So this is the initial state we were in. This is the action we took. This is the reward we received. And this is the state we ended up in. So you're right, ST1, because it gets equal to ST, it's here. And then it's the same case with, so this is the action we took. This is the reward we received. This is the next state we ended up in. And then this next state ends up right here. Good. Okay. So you're right in that it does get stated twice, but we did this for our own convenience. This is by no means the way you have to do it. This is just how I like doing it, because it's easy for me to when we're doing the training, it's easy to just have the next state there, instead of having to sample, like, get the next time step and then do it like that. It's just nice to have this next element, the next state, as an additional element in this time step. It's about convenience. By no means is this the way you have to do it. You can, if you please by all means do it some other way. But this is just, I would prefer if you. Yes. Yeah. So yeah. It is okay because we all initialized random policies. We all initialize random policies, and your policy is not the same as my policy. So yours might be taking a different actions, and you might have ended up in a different initial state because the initial state is random. For your question, for Prazi, yeah, it's a 2-dimensional array where the first dimension, the rows, are the time steps, and the columns are ST, AT, RT, ST1. And then this is going to be time step 2. So this is essentially S2, A2, R2, R3, S3, etc. Yeah, so we formatted it a little differently. The trajectory is actually 1-dimensional, but we formatted it so that it was 2-dimensional for our own convenience. All right, let's proceed. Hopefully that's clear. Hopefully we're all okay. Here we go. Let's get to some mathematics. Any questions? Any other questions? Are you guys all caught up? Okay, let's keep going. So now we're going to define a couple terms and a couple ideas, a couple concepts that the Bellman equation it comes up. Okay, so here what we're defining two ideas. One is the horizon, which is referred to as h, and this is the number of time steps in each episode. So h can be a just a natural number, right? A number between a zero and I'm not sure if zero is a natural number, but a number between an integer greater than zero, or it can be infinite. The horizon can be infinite, and that is how we define non-episodic problems. Markov decision processes in which the horizon is infinite are considered to be non-episodic problems, non-episodic reinforcement learning problems, and the solutions are the we're just going to stick with episodic problems today, but you can apply these things to non-episodic problems. It can be extended to non-episodic problems. All right, so now we're going to define something called the return. Now the return is the discounted sum of rewards from the current time step to the horizon. Now the return is the thing we care about in reinforcement learning. It's the reward, but the reward from now to the horizon. We care about the reward, but not just the reward right now. We care about all the rewards that we get from now to the end to the horizon. So in reinforcement learning, what we try to do is we try to maximize this return variable. And what this return variable is the sum of rewards from t to the horizon multiplied by something called a discount factor. Now this discount factor is essentially a variable that tells the agent how much to care about future compared to current rewards. So because the agent is trying to maximize this thing called the return, this is the summation, changing this gamma value actually changes the return and causes the agent to maximize different things when the gamma value has different values. So let's dive a little deeper into this gamma value and see. So that's the horizon. Yeah. Okay. So let's probe a little deeper. Let's try setting the gamma value equal to 0. Excuse me. Oh, sorry. Excuse me. So what happens is the return reduces just RT. So we have RT 0 to the power of 0, which is just 1. Then RT plus 1, 0 to the power of 1, which is 0. So this cancels out, and everything that comes after cancels out. So when gamma is 0, essentially what we're telling the computer, what we're telling the agent, is that the return, the thing you're trying to maximize, is just equal to the current reward, is just equal to the immediate reward. So yes, yeah. So this is so the discount factor. Human beings act as if we have a discount factor. We tend to weigh future rewards in different amounts compared to current rewards. So what's an example of this? Most of you guys are probably in university, right? I think, yeah. And so what we're doing is we're actually taking a negative reward. Like this isn't easy, right? It's not, for some people it's fun, for some people it might not be that fun. And what we're doing is we're taking this negative reward in anticipation of some future reward. So this will become more clear as we explore different gamma values. So a gamma value of 0.5, it has the effect that it has on the return is that it it still considers the future reward, but not as significantly as the current reward. So when we set the gamma value to anywhere between 0 and 1, not including either, what we essentially telling the agent is that, hey, I do care about the future reward, or you should care about the future reward. You should be maximizing the future reward. Current reward is much more important, or the current reward is more important. So so when we set the gamma factor to something between 0 and 1, we encourage the computer to learn to take actions that also take the future into consideration. So this might be important for board games. It might be important for a stock trading bot because we don't just care about the now. We care about winning. We care about making money in the future. Although we might lose money now, what we care about is making money in the long run. Although we might lose a piece or something like that now, what we care about is winning the game in the long run. So, but if you were to set your gamma to 0 for like a chess bot, for example, your bot would just go after any material right away because it's trying to maximize that immediate reward, and it wouldn't care about the long-term implications of the move. It wouldn't care about whether it wins the game. It would just care about whether it took your pawn or your piece or something like that. But if you set it to something greater than 0, it takes into account these future rewards. It values them in its summation of in its calculation of the return, which is the thing we're trying to maximize. All right. So what does a gamma factor of 1 look like? A gamma factor of 1 actually reduces to just RT plus RT plus 1 plus RT plus 2, all in equal proportion. So when the gamma is equal to 1, essentially what we're saying is, what we're telling the learning agent is the future rewards are just as significant as the current rewards. $5 in the future is just as valuable as $5 right now. That's what we're telling the that's what we're telling the agent. It may not be the case. I don't know. It depends on how you define the problem. This is something that you can tune. This is a hyperparameter that we adjust so that we get the type of behavior we want out of our learning agent. And this is something that you and I have. You and I behave in some way as if we have this gamma factor. I'm sure we know people who, I'm sure you all know someone who has a gamma factor of 0. Like, this person does not care about anything after today, anything after right now. It's just about right here, right now, yada, 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 right? It's not, the person doesn't care about RT plus 1 or RT plus 2. These might be very negative. RT plus 1 might be like negative 100, but the agent doesn't care because it's just trying to maximize this. Most of us fall somewhere between this range, right? Somewhere between 0 and 1, where we know that where we are taking the future rewards into consideration. What is the range of gamma? So that's a good question. 1 second. Sorry, oh shit. Okay, so I saw the last question. My chat just got cleared. Crap, but so I think the last question was what is the range of gamma? Gamma is 0 between 0 and 1, including both. You can't have negative values because when you have negative values, your future reward gets scaled in a way that is unrealistic. So let's say you have a gamma of 2. What that means is you're essentially saying is this would return to RT plus 1 times 2, which is telling the agent that the reward that you get at T plus 1 is actually double what you actually receive. It's not the real reward. The reward, so when the agent gets to RT plus 1, it's not going to get that 2 times factor. What it gets is actually just RT plus 1. So when you have values greater than 1 or less than 1, what it does is it scales the reward in a way that isn't real, in the sense that those aren't the rewards you're going to receive. So the value has to be, it's constrained between 0 and 1 because any value greater or less affects the reward in a way that isn't real. Hopefully that's clear. In a way that isn't real, I guess that's. In a way that isn't true. I think that might be. Can you not have a gamma greater than 1 that biases towards the future? No, because it's a lie. So say you have gamma equals to 2. This turns into RT times 1 plus RT times 2. So what you're saying is this is the reward you get now, plus the reward that you get tomorrow is actually twice what the actual reward was. So say you invest $100 into some company, and you know that next year you're going to get dollars back. So the reward would be plus 500. but it would be multiplied by some discount factor. That might be the interest rate or something like that. But if you have this greater than 2, what you're saying is you lose $100 now, but you actually gain $1,000 in the future, which is just not true. You don't gain 1,000, you gain 500. So when you get to the future, you're not really going to receive that 500, that 1,000, you're going to receive 500. And this affects the return value. It makes it false. It changes it so that the agent, it will change the way the agent behaves, and that might not be best for its performance. It won't get that 1,000 reward here for sure. It would get 500. So setting it to be greater than 1, yeah, I think I hope that's clear. Let me know if that was clear. There is a bit of a delay, so I don't know if you guys are. Okay, let's keep going. I'll come back to that if you guys want me to. So here we go. So we're about to define another main component of the learning agent, and this component is called the state value function. The state value function, denoted v pi of s, is the value of a state is the expected discounted sum of rewards that you will get if you follow policy pi from the state from the state s at time step t to the horizon. Okay. Great. So what this state value is essentially telling us is the average return we'd get if we were to go through like an infinite amount of episodes. So if we were to continuously play a chess game using this policy pi, right? This is important. It's the expectation, it's the average by following this policy pi. It's the expected return, the average return we'd get if we follow this policy. So why do we need something like this? Don't we have the return? Isn't the return sufficient? We need something like this because this function allows us to compare two different policies to determine which policy is better than another. So say we have one policy v pi 0, and then we have another policy called v pi 1. Now, if v pi 1 has a greater expected return for each state that the agent can be in, we can say for certain that that policy is better than the other because the expected value that we're going to get is much higher. So this function allows us to compare and select between different policies, which is very useful when trying to determine the optimal policy. All it is just the expectation of the return by following policy pi. The average return you'd get if you follow policy pi from the state to the horizon. Okay, it's 5. Yikes! Oh, yikes! I have to. Let's speed up a little. Okay. How many slides here? Okay. So here's just a visual that we use in reinforcement learning, referred to as a backup diagram. So this backup diagram is just a way of visualizing the trajectories that an agent can go down when interacting with the environment. So this could be a game of tic-tac-toe, this could be a game of chess, etc., etc. And the trajectory that the agent goes down is determined by the policy. And what our objective is in reinforcement learning is to determine which branch to go down, which branch provides us with the highest return. And then the value tells us the average return that we'd get by following policy pi from this state. So if this policy always leads us down this branch, then the expected return is just the sum of rewards gotten by going down this branch. But if it goes down a bunch of other branches, what the expected return is just the average return that the agent would get. Okay, I'm gonna speed up a little bit. But please just keep asking questions if you have them, and I don't mind going back and clarifying. So let's look at an example of this backup diagram to get a better sense of what this value is. So here we have the backup diagram for a tic-tac-toe game. Here's the initial state. It's always the same, regardless of what game. It's not random. And I skipped a couple of time steps to simplify the diagram. And this by no means is the entire diagram. There's many more actions and many more states that the agent can go down. But just to simplify it and keep it clean, I limited it to just these couple. These game trees are actually huge. Here's just a fun fact for you guys. The game tree for chess has more trajectories. There's more pathways down the game tree for chess than there are atoms in the universe. That is insane. But that's just a fun fact. Okay. What the value tells us is that if we follow this policy, what's the average return we're going to get for from this state? So say we're trying to find the value of state st. And our policy is just take this action, go down this branch. Right? The policy is when you're in this state, this particular state, take action A1, which is just putting an X here. It's not the best policy, it's actually it's a really shitty policy. So the expected return would actually be -10. Because that's the sum of rewards that we're going to get from this state to the horizon, to the terminal state, by following that policy. Alright? If the policy actually let us down a couple of these branches, maybe it let us down this branch and this branch equally, like 50% chance going down this one, 50% chance going down this one, it would be the average of the two. So it would be, it would actually just be 0. Yeah. So so it depends on the policy. The value of a state depends on the policy used to go down that trajectory. So now what I'm going to introduce is something called the state action value function. Now the state action value function, which is called the Q function, is what we use to determine the optimal policy. So what the state action value function is the expected discounted sum of rewards that you will get if you take action A in state S and then follow the policy. So this one's a little different. It's pretty similar to the value function, but instead now what we do is we take an action first. So we don't listen to the policy for one time step. We take this action, then we follow the policy. So let's see what implications this has. So now let's try to evaluate the Q function for this state. So the Q function is actually a function of the state and the action that the agent could take in that state. So here there's actually 3 Q values. There's st a0, st a1, st a2. And all 3 of these have different expected returns. So what this Q value is saying is take this action in this state, then follow this policy. So if you were here and you took action a0, then you follow the policy, the expected return you would get is the Q value. As same goes for this one. In this case, it's actually just -10. So the Q value of sta1 is -10, and the Q value of sta2 is +10. So why do we care about this thing called the Q function? So the Q function is actually very useful, and because it allows us to determine a better policy. So say we have the true Q values for all of these state action pairs. We have the Q value for this and this and this. So this one is like -20, this one is -10, and this one is +10. If we have all of these Q values, the policy is actually very simple. The policy would just be take the action that gives you the highest Q value. Because what the Q value is the sum of rewards you're going to get by taking that action, then following that policy. So if this is -20, this is -10, and this is +10, the policy is simple. The policy is go down this branch because the expected return is so high. So that is essentially what Q learning is. In Q learning, what we do is we try to learn this Q function for all state action pairs, and then what we do is we extract a policy from this Q value. We look at the Q values for all state action pairs, and then we just take the action that gives you the highest Q value in each state. So for state ST, it would be A2. So the optimal policy we just determined is actually taking A2 in this state. Alright, I hope that's clear. I'll slow down a little. Let me just quickly check what's yeah, so we're almost done, almost done. So this was the main, so beautiful, yeah. Not policies, Q values. So you're close, Prazi. So for the taxi driving example, we would have to look at 500 by 6 state action values. Each of these state action pairs has a different value. Not a policy. The policy is it's a different thing. And then from these state action pairs, we can extract the policy. So just say for one of these 500 states, for each of these 500 states, we would actually have 6 different Q values. And what all of those Q values tell us is the expected return we'd get for taking that particular action in that state. Then the optimal policy is obvious from there. Is just the yeah, no, the values are right. Yeah, the values are right. Okay, let's keep going. So now what we're going to look at is something called do we have a no, so after this next slide we're going to write up we're going to write up Q learning, and then that should be and then we'll see from there. Okay. So what I'm about to introduce is something called generalized policy iteration. Now what this is the general idea of determining by the optimal policy by letting the processes of policy evaluation and policy improvement interact. So this general idea is a lot of reinforcement learning algorithms can be described as examples of or instances of this general idea. And in this general idea, what do? We start off with a random initial policy, which we already have. Then what we do is we evaluate it. We determine, in this case, the Q value function. You can do the value function too, but we're just picture a Q here. So what we do is we evaluate the policy. So we determine the Q function for that policy, and then we use that Q function to improve the policy. We actually improve the policy by using all that Q value that we just learned, we just evaluated, and then we continue this process for as many time steps as we need. And what ends up happening is that we end up converging to the optimal value function and the optimal policy. These are so there's just two interacting processes here, just the process of evaluating a function and then the process of improving the function. And then we let this run for some number of time steps, and then we end up at the optimal policy. So the different algorithms differ by just how often you improve the policy, how you evaluate the policy. So it's just the details that differ. But the main idea remains the same. You have a random policy that you initialized, you evaluate it, you improve it, and then you evaluate it again, you improve it again, and you keep iterating until you converge to the optimal policy. And now what we're going to do is we're actually going to implement it now. So forget the last slide. It's not really necessary. So this is the algorithm for implementing something called Q learning policy evaluation. So this is a specific type of policy evaluation. To be more specific, it's a temporal difference method for learning the policy, for evaluating the policy. I don't really want to get into the math behind this, but so I don't really want to derive this, but I've made a Google Doc of a bunch of resources for you guys to look at if you want to keep studying this stuff. And you'll see this derivation pretty early on in your study of reinforcement learning. But for now, we're just going to assume this is true. Assume this is the the equation for improving our estimate value function. All right, great. So I'm gonna leave it up, but I'm gonna pull it back up. But here is the the Q-learning function. It takes as input the policy and the number of episodes to run for, and then what it returns is the improved policy as well as the Q value function. But the first time we go through this, what we're going to do is we're not going to do any policy improvement. We're just going to evaluate the Q function. So the policy remains the same in this case. But after we evaluate the policy, we're going to write the line of code that improves the policy. And then after that, we will have just one more step to have completed the learning agent. So here's the code. Forget about all the commented out stuff. We'll get to that later. Here's the code and here's the algorithm. You have everything you need. The functions are in the cheat sheet. Go ahead and try implementing Q-learning policy evaluation. This one is actually a little difficult, but you guys can figure it out. Ooh, I think I missed one. I think I missed a function for you guys. I think I missed the numpy.zeros function. You know what? Just Google it. There's a function in there called numpy.zeros that I did not include in the cheat sheet. So I think you just Google numpy.zeros and you should see the docs. And then just from there, just figure out what values you have to put in. You know, I should just All right, guys. I'll give you like 2 more minutes, and let me know if you're missing another function. I don't think you guys are, but I haven't looked at solution, but I'm confused about what to do about max Q. I think hmm. I'm looking now at the max Q part, and it is a little unclear. But essentially, what we want to extract from that is the max Q value of all the actions that you can take in the next state. So you would input the next state, and then get the max Q value from whatever you extract from whatever gets outputted by inputting the next state. I didn't want to. I'm not trying. I'm trying not to give it away. But I'm trying to give you a hint. Hopefully, I didn't confuse you some more. Uh, but that's a difficult part. I don't know. I'm not sure. I don't know. We'll have to wait and see. Okay. All right, guys. Drop a lol in the chat if you guys are done. Drop a. Let's see a lol. Nice. Good. No, I don't think so. Like code, right? Like VS Code. Uh, no. Okay, one second. All right, let's keep going. Okay. So hopefully hopefully that wasn't too hard. So this, uh, can you guys see the screen? Let's put this up. Okay, so we have this Q-learning function, and we're inputting the policy, and what we want for now is to evaluate this policy using something called Q-learning. I showed you guys the algorithm for it. I didn't derive the algorithm, but uh, but that is the algorithm for Q-learning. Okay, so we're initializing here something called the Q function. Now, because our state space is small, we can actually represent it as an array, as a matrix. A matrix of size number of states, so number of state rows, so 500 rows by number of actions. So 500 by 6 matrix, where each value, each element, is the expected return that you would get for taking the action, which is the column you're in the state, which is the row that you're in. So what we want to do in reinforcement learning, or in Q-learning at least, is we want to learn this Q-value function. And once we know this Q-value function, the policy is easy. The policy just becomes, just take the action that gives you this maximum reward. Just take the best action. So the objective in reinforcement, in Q-learning, is to determine this Q function. And that's what you guys just wrote. You guys just wrote a function that does that. So here we have st is equal to environment.reset. Great. At, this we saw before. At, policy, st, right? Policy st. st1 rt done debug is equal to environment.step at. That's also pretty clear. Now old value. What is the old value that we are planning on updating? So because we just encountered state st and at, we're going to use the information we just sampled, using this reward signal that we just sampled, as well as the next state that we encountered, to update our estimate of this Q function. So we started with the initial estimate of this Q function as just a bunch of zeros. Now this isn't the true Q function. So what we're going to do is we're going to iteratively converge to this true Q function. So what is the procedure for doing that? The first is determining what the old value was. So this is just Q value st at. So what this does is it goes to the matrix that we initialized above, and it pulls out the element, this element that is referred to by these coordinates. Meaning, what is the expected return that we're hoping to get in this state action pair? And then we use that new value and we improve it. We update it. We update it by using something called the Bellman equation, in which we add to our old value this value times the learning rate. Now this value is calculated by RT plus numpy.max Q value function st1. Alright, so what this is essentially saying is take this thing, which is our improved estimate of the next Q value, subtract the old value, so essentially get the error between our new estimate and our old estimate, multiply it by some learning rate, by some step size, and then add to it the old value. So what essentially happens over time, over iterations, we slowly we converge towards the true Q value. And then once we have that, the policy becomes easy. And then the Q value function, now we update the Q value matrix by referring to the STAT element and making it equal to this new value that we just calculated. All right. Any questions? Are you guys clear about, maybe you guys are focused on the values, making sure you guys are getting that right. So to check if you had the right, if you did it right, we can actually just run this. So what we can do is we can run this cell, right? Go up to here, click play. Why for old value is it st? So we just encountered that state and that action. So right now, what's going on in this for loop is that the agent is interacting with the world, and at every time step, we're updating the estimate of the Q value using the information we just observed. So we encountered a state. Do we have? Oh, and this st1. st1. So we encountered a state and we took an action. And after we did that, we received a reward and observed the next state. Now we use this information that we just sampled to improve our estimate. Yeah, so st is the first index because this is the row, right? We're essentially saying the st row, which might be the 50th row, the 300th row, and the at column, which is just 0, 1, 2, 3, 4, or 5. And we say update that value. So update our matrix of the Q function, update our current Q function to improve it, so we get a more accurate Q function that is more representative of how the world works. That is just a more accurate Q value function. And why are we doing this? We're doing this so we can extract the optimal policy from this. I hope that's clear. Ooh, what? Oof, I messed up. Q value function. Hopefully. No. It's numpy.zeros, number of states, number of actions. And there's 2 brackets here. That's something you guys have to be aware of. There's 2 brackets. This is actually shapes. I think it's like this. Yeah, so this is the shape of the zeros array is equal to number of states by 500. 500 by 6. Okay, we are going to proceed. Okay, now what? Now let's actually run it and see what the Q value function looks like. So we're gonna run it with the initial policy, and we're gonna add a cell. Initial policy is not defined. Let me just fix that. Sorry. I didn't run all of these. Run. I'm actually gonna add another code block beneath it. Yeah, you had the shape right before, Prozzy. You actually said the right shape up here somewhere in your question. But then I don't know why you did 1 comma 50,000. That doesn't make any sense. But the one before was right. The shape before you said was right. Not that long. It's gonna take a couple of seconds, maybe like 30 seconds. We can actually just decrease the number of episodes. But for now, it should be fine. It should be fine. If we're breaking. So while this runs, we're going to look at the next step. Now we have a queue function. Now what we're going to do is use this queue function to determine a better policy. So this step is referred to the policy improvement step. So in policy improvement, what we do, or what it is, it's the process of monotonically improving the current policy. So what monotonically improving means is that the new policy is just as good as or better than our old policy. It's not possible for our new policy to be worse. We're not going to go into the proof for that, but I'll give you guys some intuition. Because we have this Q value, and we take an action that kind of sucks, if it's a bad action, there will be a low Q value. So when we take the argmax, the action we take won't actually be that bad action. It will still be a relatively good action. So because of this argmax, the policy never gets worse. It either remains just as good as it is, or it gets better. And that's great, because if we let this run forever, it will converge to the opposite. Some other conditions. Hopefully this shouldn't be taking this long to run. Maybe I think there might be a mistake somewhere. I'm gonna change this to 5,000 and see if that improves it. Ooh, this shouldn't be taking long. Oh, maybe I'm just not patient. Yeah, it's been running for over a minute. It doesn't. Let me. There might be a mistake in here. Yeah, so it just takes long. So let me just print the Q value function. Dot shape. So if your shape of the Q value, so you can go back to the Q value function parameters and change this number of episodes to a much lower number, maybe like 500. When we run it with policy improvement as well, we're gonna run it for 50,000. Because then we actually want it to converge. Right now what we're doing is we're just implementing the Q-learning policy evaluation. So what this function returns is the policy, which we inputted, the policy we haven't changed, and then this thing called the Q-value function, which we just we talked about. So what we're going to do is we're going to print the shape, and we can actually just print the Q-value function. It's not going to print the whole thing because it's such a big array. I think there's a function for that. NumPy print entire. It's okay. But just what we have here is just a 500 by 6 array, each with values of the expected return at that particular state action pair. Now, if you guys actually look at all these values, a lot of them are still 0. And that's because our agent has not, the policy of the agent hasn't changed. The agent has not gone to any different states because its policy never told it to. And because we're not changing the policy, it always ends up in the same couple of states. What we want, though, is we want to go to every single state action pair. Because that way we can determine a better Q value function, and the better our Q value function is, the better our estimate is of this Q value function, the better we can improve, the better our policy improvement will be. Okay, great. So yeah, no, that's okay. It's supposed to be different because our policies are different. Our policies were random, and our policies are what determine which states we end up in. As long as the shape is what's important. If the shape is is 500 by 600, you guys did it right. If the shape isn't 500 by 600, if 500 by 6, I should say, then you guys did it wrong, and you have to just check for an error in your code. All right, so now what are we going to do? So now we're going to implement this policy improvement step. So what this step is, it's just one line of code. That's okay. So what this policy improvement step, it's simple. It's saying a better policy, a new policy, our improved policy is just equal to, for this particular state, is equal to the argmax of q pi I of st. So we refer to our q function and we extract all the q values for all the actions we can take. So in our case, it would be a vector of size 6. And then what we do is we just take the argmax. We take the argument, which is just the index of the action that gives us the highest return. And then there you go. We got a better policy. So what you guys are going to do is you guys are going to actually implement that right here. We're going to uncomment. Just going to fix that. So we're just going to pull this out of the oh shit, out of the we're just going to pull this out without without ruining the, we still want to leave the stuff commented out. And then I want you guys to write this line. So essentially we're improving the policy here. So how do we improve the policy? What is the, you guys have to figure out how to what to write here. And this should help. Alright, so this one should have been pretty quick. Let me try to so this one is pretty easy. We're running a little short on time. I don't want to hold you guys after the end of the workshop. So this one is just numpy.argmax q value function. This is st. So what this q value function returns, we actually have it down here. So this, don't worry about typing this. This is just for me to show you. So we have q value function, and just to say for a random state like state 23, what it returns is a vector of 6 different values. So this is essentially what this is saying is that when you're in state 23, which is just one possible configuration of the world, right? We don't know exactly which, but we know it is one. There's 6 actions you can take. And here are the expected returns you're going to get for taking action A0, A1, A2, A3, etc. So this might be going up, this might be going down, this might be pickup. So when you have the true q value function, this will tell you the expected return that you're going to get for taking that action. Right now ours isn't really that good of an estimate. It's all zeros, which it shouldn't be. And then once we have a good estimate, the policy is simple. You just take the argument of the one that gives you the highest return. Okay, great. Almost. So now what? Now let's actually run this. And while it's running, so we'll come back and change this back to 50,000. And we're gonna run it. Anyone running into any issues? Are you guys all right? If you oh, it ran. Okay. No issues. Good. Okay. So it actually ran pretty quickly. Now no issues. Okay, very good. So that actually ran pretty quickly, and what we're going to do is we're actually going to add another code cell down here, and we're going to generate a function using this improved policy. So we should actually have written improved policy here. It's okay, leave it for now, because during this loop, during this function, what we were doing is we were updating the policy. So the policy we copied here, this initial policy of ours, we were continuously updating it and changing it. So theoretically, at least, what this should have returned is a better policy. Or at least, or maybe even the optimal policy. That's what we would want, ideally. So what we're going to do is we're going to write generate episode using that policy and render true. So we can see what our policy looks like. Oh, and it actually, it worked. It shouldn't have worked, which is funny. Um, there's a uh, it worked, but there's another thing that we have to introduce that is important to reinforcement learning. Here, I know why it worked. It wasn't supposed to work, but it worked. It wasn't supposed to work because we weren't exploring different actions. So if you guys ran it, did you guys successfully, did your taxi successfully drop off the guy? Did you receive this drop positive 20 reward, or is yours like 200? It's different for everyone, right? It might not have worked for you, it might have worked for some. Me, I just got lucky. Oh, it did work. Okay. Okay. Okay, so that's it. Okay. Uh, it worked. Great. So we arrived at a better policy, but this might not be the optimal policy. If you run it again, okay, the agent is doing pretty well. But there's just one other thing that I have to introduce about reinforcement learning. Um, this environment is actually because we receive negative rewards and we can have negative values. We actually still explore, which I can explain why, but we're just going to keep going. There's one more thing that we have to implement, and that is something. There's one more thing one more concept we have to explore, and that's called exploration versus exploitation. Now, in reinforcement learning, what we want is we want the agent to find the best policy. We want the agent to find the best trajectory, right? We want the agent to, yeah. So if you just have a static policy, meaning a policy that doesn't change, it's never going to find the best policy, because it's just going to keep doing what it always did, and it's never going to try different actions in different states, which means that it's never going to find actions that are better than other actions. So in reinforcement learning, this is one of the main trade-offs, or main ideas. It's this constant battle between exploiting the strategies or policies that you already know work. So this comic is actually a very nice representation of this. This robot is there's a fork in the road for this robot, right? He usually goes to this usual place that he knows is good. He knows this place tastes good. Now he can try this other grand opening place, this brand new place, but this place might suck, right? He doesn't know whether this place is good or not. So what the agent has to do is the agent has to choose whether to explore, so go to the grand opening, or just exploit what it already Yeah, we'll try something else. Discord was a good option, but it was limited in capacity to like I think it was anticipating a bit more. But next time, if we know, we might restrict the size, and then just do it on Discord. Uh, okay, great. Hopefully you guys are all here. Uh, back online, great. Yeah, we'll just probably do a smaller group one. Okay. We just have to explore. We just have to implement this exploration versus exploitation thing. What we want is we want the agent to explore actions it hasn't taken in states it's already been in, so that it actually finds the best policies. And what we want is we want over time this epsilon value, this rate of exploration to decrease. All right, so how do we do this? We do this by using something called the E greedy policy. So E or epsilon greedy policy. So what the epsilon greedy is just a policy that has a variable called epsilon, which is just a number between 0 and 1. And what the policy states is that pick a random action with probability epsilon, and then be greedy with respect to the Q function with probability 1 minus epsilon. So if epsilon is 0.5, what we're saying is half of the time pick a random action, and then the other half of the time choose the action that gives you this highest Q value. So this is our best approach to explore. In our particular environment, it was easy because the agent explored on its own, because of how the Q value function looked like. But most of the time, in most environments, you have to implement this E greedy policy to get the agent to explore. So what we're going to do is now we're going to implement this Q E greedy policy by just uncommenting all of this stuff. We don't really have time to go into all of it. We just remove the comments, and I'll go over it a little quickly. Of these, there's three different comment blocks. One is in the hyperparameters. One is this if-else statement, and one is this if numpy.random. Alright, so we declare this epsilon, we declare our hyperparameters up here in the top of the Q learning function, and we declare this variable called epsilon, which determines the frequency with which to take random actions. And we also decay factor, because we want this epsilon factor to decay over time, and we have this minimum factor that puts a lower bound on how small the epsilon could get. So so that it doesn't just keep decreasing to 0, and that we also still want a little bit of exploration happening, because it still might be that the agent should still explore a little bit, because it could still find better policies. So here we declare these hyperparameters. Then if you scroll down, here is where we decay the hyperparameters. Essentially say that if the epsilon is greater than this epsilon min, decay it, which just means multiply it by the epsilon decay, and then assign that value to epsilon. Okay, and then else epsilon is equal to epsilon min. So if epsilon becomes less than epsilon min, just make it equal to epsilon min. Then everything else is the same. We all wrote this together, or you guys wrote this. Here this is our old line of code for improving the policy. What we're going to do is just comment it out. We're not using this line anymore. We're using this in this if-else statement. So really, you could just delete this. It's up to you, but you just make sure you remove it. I'll leave it there so you guys know to comment it out. So then what we say is if numpy.random.random, which just generates a random number between 0 and 1, a random float between 0 and 1, if this random number is less than epsilon, this is a random uniform distribution. So a random distribution between 0 and 1. If that number is less than take a random action. Sample an action from the action space. This is how we do random actions. We do environment.actionspace.sample, and this just samples a random action. So we're saying essentially with probability epsilon, that's essentially what this is saying. Take a random action. Else, do this argmax thing that we wrote up here. Alright, so if you guys did that properly, if you guys, then this should run. And we're going to go back up to this Q learning and put this back to 50,000. If you don't do it for long enough episodes, it might not converge to a optimal solution, or to the optimal solution. Alright, here we go. So now we're done. Now you can run this, and here instead of writing policy, what you can do is you can write optimal policy. It might not be the optimal policy. It might still be able to improve because convergence is guaranteed in the limit. It's guaranteed if you iterate this for an infinite amount of time. So, but it's going to be pretty good. It's going to be good enough for our purposes. So now we're going to run that, and that's going to take some time to run, maybe a minute or so. And then what we're going to do is we're going to delete this generate episode line. We're going to delete this cell, and we're actually going to run this cell called watch. Now what this watch cell does is essentially generates an episode, but it has this sleep thing where it allows you to watch as it generates the episode. So after this is done running, which is just finished, what you guys should do is you guys should run this watch cell, and then copy the name of the policy, the name that you gave to the policy, and then input that into the watch function. And what I want you guys to do is I want you guys to run this function, and then look at the actions that the agent takes, and compare it to yourself. So look at the state that the agent is in and ask yourself, which action would I take in this state? And then compare yourself to the action that the agent takes. It might not be the same, but that's not the point. The point is, we'll just run it, and then you guys will see. Oh, he actually started at the right one. Okay. Damn, there we go. So I know it looks simple, or I know the environment isn't that complex and all these things, but what we did is actually pretty profound. What we did is we just took this computer, this literally just this inanimate object right here, and we somehow trained it. We just through some simple operations to yeah, sure, we'll use something different. So we just use this by just we took this inanimate object, this computer, and then we trained it somehow using just some simple few lines of code, right? This is just it's barely 100 lines to learn how to act in a world in the best possible way. Now we took a machine and it's taking the actions that you most likely would have taken in the same state. Now although the the environment is small, this idea and this technology can be extended to very complex environments, or at least much more complex as this, much more complex than this, and it might potentially be able to be uh, applied to real world applications. It is applied in self-driving cars and all this other stuff. So what we did is we just took this inanimate object and trained it to behave like it was intelligent, which I think is amazing. And yeah, so what you guys learned is called Q-learning. And if you guys were to combine this with neural networks, it becomes much more powerful. So what I'm going to do is I'm going to show you guys a little demo of this same thing that you learned being applied to a much more difficult problem. Let's go here. 1 second. Okay. 1 second, guys. Okay. We're gonna go. Okay. Drew. So we're just gonna run this demo that takes the model files. Yeah, okay, let's run this. So we're just gonna run this demo, and what it's gonna do is it's gonna show you our learning agent at different stages of learning. Sorry, okay. So hopefully you guys can see. So this is our random initial, like, random policy, and it sucks, right? It is getting one or two of them. Actually, it's getting a couple of them. Oh shit. But oh no, I think I'm. No, I ran the wrong thing. Let me just comment this out. This is not the. I think this is the trained. Regardless, I don't know where the. I don't know where the initial model is, but just picture an agent that sucks, right? Okay, so just picture a random agent that's just behaving in a way that just taking random actions. And what we did is we applied Q-learning, right? It's the same thing. A lot of it might look familiar to you guys, but we just use something. We just use neural networks on top of it. What we did is we just took we just used neural networks. So this is just we just declared this neural network using Keras, and we trained this neural network to play this game using Q-learning, using deep Q-learning. And this is just an application of what you just learned to a much more complex environment. Are you guys still here? Okay. Yeah. So although so we trained this, we wrote this ourselves at the RL department, but we didn't really get to train it all the way. We only trained it for a few hours, and to get it to the most optimal policy, you would have to have trained it for like a few days almost. So I'll show you guys an example, or I'll show you guys a fully trained one. Kira's breakout example. Just to show you guys the application of this stuff. So this is using the same thing that we just learned called Q-learning. It trained a learning agent to play breakout. So this was before training, where it just sucks. This is early stages where it is playing decently, and then this is the late stages where it's playing at a superhuman level. It actually figures out this very cool strategy of making a hole on the side of the wall and then just launching the ball through that hole, and letting the ball bounce around on its own, which is very cool. Um, yeah, so this is something we've been working with at the RL department. Yeah, right here. It's gonna make a hole right here in the left side. Yeah, that's so cool. And then the ball just hits all of them again. Yeah, and it just does it by itself. All right. Is there any way to determine when something has been trained enough? Can Taylor approximations be helpful in determining how many iterations before certain error threshold? Hmm. I'm not sure I know what you mean. For these environments, the person who made the environment actually defines when it's done, or when it's solved. In the case of this breakout problem, I think it's 40. If your agent scores above 40 points on average, so if you do if you do 100 episodes and the agent scores above 40, the problem is considered to be solved. Uh, so our agent was doing it around 20 or 30, so train it long enough to have completed the problem. But if we had run it for a couple more hours or maybe a day or two, it would have reached this point of this score of like 300. I don't know what you mean by using Taylor approximations to determine how many iterations. Uh, I'm not sure what you mean, but it's much more just trial and error, just running it and seeing how well it does, and then tuning the parameters to improve the performance. All right, guys. So that's the demo. It's because we went over time. I couldn't have spent more time on it. You guys can watch it again, actually. So while this is playing for you guys, so this is one of our better models. It's not loading the shit one for some reason, but this is one of our better models. While this is going on, I'm gonna pull up one more thing, which is just an announcement for an event we're having in the fall. Here we go. Okay. Are you guys still there? Uh, I mean, like how Taylor series are used. All right, so this is a teaser trailer for an event we have coming up. We're actually developing a game called Alula, and what we're gonna do is we're gonna host a challenge, a reinforcement learning AI versus AI challenge, in which people will program their own learning agents for this game, and the agents will compete with each other. And whoever writes the best agent wins. All right, so this is just a teaser. Yeah. So what is Alula? Alula is a palindromatic name of the very first double star, which is identified as one that is physically related to its twin. So it also means the first step in the first leap in Arabic. So these are just some hints about what the game might look like, and what we hope to achieve with this event. So it's an AI versus AI competition in which we program a bot to compete with other people's bots in an epic tournament of bots. uh, right. Okay. So here is a teaser image of the game. So it's a score-based game with a leaderboard, and the bots will compete indirectly. So it's essentially single player. And whoever gets the highest score in the game is the winner. Whoever's bot gets the highest score in the game is the winner. Um, yeah, so you can train your bot locally, but depending on how complex the game is, we might give you guys access to uh, to some AWS instance to train your agents in. For just for the challenge, not yeah. So to prepare for this event, you should have some programming experience with Python, some knowledge of machine learning, so maybe some basic knowledge of neural networks and stuff, and then some machine learning libraries like the ones we use today, like NumPy. We didn't really get to use TensorFlow and Keras, but these are just libraries you'll get familiar with as you start to learn more about machine learning. And here's some setup documents that we'll share with you guys. This is just for getting set up, just for the roadmap of what the competition looks like. And here is a setup of a document for getting set up to compete in the challenge. So we'll put these in the folder, in the drive folder, for you guys to access. And then we will release more trailers more teasers in the future. We hope to have the game finished by the 31st, and the competition should be sometime in the fall. And and please sign up for our email list to stay up to date on all this stuff. All right, great. And I also in the drive folder I put some learning resources. Now, if you are interested in interested in learning about reinforcement learning and neural networks and deep learning in general, there's some great resources in here that I highly recommend. These are the resources that I use to get started. Maybe there's better resources out there, and you know what? If there are, add them to the list. Maybe I'll give you guys write access to this, and we'll create some sort of directory for resources for learning this stuff. Maybe there's already something like that, but these are just the resources that I personally used and I found very helpful. So these are the resources for reinforcement learning, and I subdivided them into different sections depending on how you learn best. These playlists are great, very good playlists, and this 3 blue 1 brown playlist for neural networks is a work of art. I highly recommend it. Alright guys, so that brings us to the end of the workshop. Forget the Kahoot. We don't really have time for the Kahoot. There's only like 8 questions anyway. Alright guys, so just to recap what we did today, we learned about reinforcement learning, and we applied it into this we applied it to this very simple environment. But what we did was actually very profound. We got the computer to play or interact with this environment in a way that you and I would interact with this environment. Now, although the environment was simple, the stuff we learned is just very powerful, and it can be extended to all sorts of environments, like driving cars, like flying planes, like being a surgeon, like being an engineer. All these things, these are all environments in which an agent acts in which we act in. And if you accept that intelligence is just information processing, if you accept that intelligence is possible to replicate intelligence on the computer, then the applications are literally endless. And it's just a matter of figuring out how to write a program that can do the things that we want it to do. Yeah, I think that's it. I hope you guys enjoyed the workshop. You know, the technical difficulties kind of sucked. That was unfortunate, but maybe next time we'll use something that is that lags a little less. I hope you guys found value in this workshop, and yeah, that's it. Thank you guys so much.